Let's take a look at how we can use logarithm to solve exponential equations. First, we need to isolate the exponential expression. And if it's not looking like what we had before, b raised to the power m, if you do not have b to the m equal to b to the n where the bases are the same, and then you say that the exponents are the same and you finish by solving. If this is not the case, then you must use logarithms to solve your exponential equation. If the base involved in the exponential equation is a base 10, you're going to use the common log, of both sides. So if you have your left hand side, let's say LHS equal to the right hand side, then if you take the common log of both sides, you will say, I'm going to say log of the quantity on the left hand side is equal to log of the quantity on the right hand side. And then you're going to go ahead and solve further. Now if the base is not 10, if you don't have a base 10, then you're not going to go with log a base 10 of both sides. Remember, common log is log over here, meaning log base 10. So you're not going to use that if the base is not 10. You're going to go with what we call the natural log. So if you have ln of something, what does that mean again? And they write it also this way. It's going to mean log base e of the quantity. So sometimes you write it with a capital L just to not think it looks like a 1 followed by an N. Sometimes you can even write it, by curling the letters a little bit, like cursive. So let's say we had a left-hand side, whatever it is, equal to a right-hand side, LHS equal to RHS. And then we're going to take ln of the left hand side and say it's equal to ln of the right hand side and proceed. And then you can use one of those properties that we mentioned before where you make the low power jump in front. So you'll have that ln of b to the x is x times ln of b. Now if you ever come to across ln of e to the x, okay, so what this is, it's which power, because that's log base e of e to the x, so which power of e, the base hanging from the letter g, will give you the quantity e to the x. So what is the answer? The answer is just x. Or just think about it that log base e and e to a power destroy each other, and what you get as an answer is that x falling from the sky. Or just cancel the ln and the e, and again you get just x as an answer falling from the exponent level to the writing level. Now if you had log base 10 of 10 to the x, which is what we mean by log of 10 to the x, because the log base 10 and 10 to a power are inverse functions of each other, you just get x as an answer. So that's what we saw before. Let's just see how we can apply that to a particular situation. Let's say we wanted to solve here for the letter x, for the variable x over here. So we notice that 134 is not a power of 5. We also notice the base is 5 and not 10. So we're going to take ln of both sides. So I'm going to take ln of the left hand side being 5 raised to the power x, and I'm going to say this is equal to applying ln to the right hand side to that quantity 134. So keep in mind when I write ln of the quantity 5 raised to the power x, I am applying the function ln to that quantity. I am not timing them by each other. It's like taking the square root of both sides, taking the cube of both sides. Basically, we are applying ln to both sides, taking the natural log of both sides. So what happens next is the following. We're going to go ahead and use a property that we have with ln or any log. Let me just rewrite the expression without the parentheses, which are really not necessary in this situation. So what we have is the following. We're solving for x, but notice x being an exponent inside a log, it will jump as, a number, a quantity. Let me say that a quantity timing what we have when that exponent jumps in front. So that's 5 times ln of the number 5 is equal to ln of the quantity of the number 134. So x times ln of 5 is equal to ln of 134. Now, I don't really need to distinguish with all the colors. I was just showing you I was applying ln to both sides. So it's really x times a quantity over here, which is a value. It's x times, let me just clean that up a little. It's x times ln of 5, which is a number, is equal to ln of 134. So just to show you that indeed ln of 5 and ln of 134 are both numbers, let me just get the calculator and I'll show you how I would solve it with approximations of those two numbers, ln of 5 and ln of 134. Then I'll go back and solve it exactly as stated. So let's just check out what ln of 5 is worth. Notice that they preset a parenthesis for us, so we close a parenthesis. So ln of 5 is a number which is about 1.6. Now, what is ln of 134? It's about 4.9. So what I could do is the following. I could replace ln of 5 by its value, its approximative value, just to see how I would handle this equation with friendlier things than saying ln of 5 and ln of 134. So let's see what we would get. So let's say we were to use approximations. I rewrote exactly my equation, and let's just do the following. Let's just replace ln of 5 by 1.6 and ln of 134 by 4.9. So we'll get over here x times ln of 5 is, over here we said ln of 5 is 1.6, so that's x times, and instead of that I put a 1.6, and that's equal to ln of 134. If I were to round that, I would call that 4.9 if I recall correctly. So if you were to replace those two ln values by their approximations, let's just think about the process. How would you solve for x? And you can always do that whenever you have a question, you're a little stuck. Just kind of see how you would do it with friendlier looking numbers. So you would say if I had x times, some number 1.6 and I want to really get x, I would just go ahead and do what to both sides? I would really divide both sides by this obstacle on the left hand side, preventing me from having x. I would divide both sides by 1.6. And I would get that x is a ratio of, the right hand side, which was 4.9, which I divided by the coefficient of x, 1.6. So if you can do that with, the approximations here, this approximation of ln of 5, you surely can treat ln of 5 as 1.6 and ln of 134 treated as 4.9. and use the same process you used. So let's go ahead and solve this time over here for x using the exact values, not the approximations. And keep in mind that this quantity ln of 5 is just a number. Remember, it's just 1.6, and 134 is also another number, which in this case turns out to be something like 4.9. So let's go ahead and do the following. If I really want x over here, since x is timing the quantity ln of 5, and that is equal to the quantity ln of 134, let's divide both sides of this equation by the coefficient of x, which is namely ln of 5. And then what I have is the following, that x is equal to that ratio of the quantity ln of 134, which is a number, divided by ln of 5, which is also a number. So instead of using the approximation 4.9 divided by 1.6, I have in this situation, when I express x this way, its exact value. So that's what x is worth. So you may say, wait a minute, we do have a property about the quotient of two logs. No, we don't. We do have a property about the log of a quotient, but not a quotient of two logs. So this is cute as this expression would look if we were to solve for x. Now let's go ahead and do the following over here. If I wanted to check, if it's working out, if you were to plug it in the original equation, it will be a little bit complicated. You would have to use what's called the change of base formula and all kind of things. But let me show you a nice little technique with the calculator that will show you that indeed this is a correct answer. Let's go ahead and use the calculator, and let me show you something. Let me set it up and I'll use the calculator. So let me go ahead and just erase over here all those practice steps that I had on the approximation. And let me just rewrite my equation that I have 5 to the power x is equal to 134. And if x, I believe that x is this answer. Let's see if it works out. Let's make sure, and we'll use a calculator, is 5 raised to the power ln of 134 over ln of 5. Is that indeed equal to 134? So using the calculator, what I'll do is the following. I'm going to go ahead and find over here, I'm going to first find what x is worth. That x is equal to ln of 134 divided by ln of 5. And then once I get that value, I'm not going to say it's about 3.04, because if you did raise 5 to the power 3.04, then what happens, you would not get 134, which is what's on the right hand side. You would get something, close to it, but not quite. So let's go ahead and not do that. Let me just type, what x is. If you press second enter a couple of times, it takes you back in your steps, and you can, recover that x is this value of ln of 134 over ln of 5. Once I type that x, I can say that x is about, if you wanted an approximation, 3.04. But let's say I want to use the exact value and raise 5 to both sides, 5 to that power. Then what would I do with the calculator to compute what is on the left hand side here? All I have to do is this with the calculator, and remember that you just do 5 raised to the power, so the exponent key, and then you do second and the little negative sign, because that's called the answer. Okay, so let me just show you what I did I did again, let me show you 5. Oh, wait a second. I did 5 raised 2 over here. The second answer, which is the previous answer with all its decimals. And if you go ahead and press enter, it will give you exactly 134, which is the answer we wanted. So this checks out. Check mark on this one.